Hey guys, I'm solving this physics variant today. This is October-November 2021, 9702 variant 42, physics paper 4. So I'm gonna do variant 41 as well very soon, by tomorrow. So these two variants were a bit difficult. 41 is the same as 43 by the way, 42 is unique. These variants were a bit difficult compared to May-June 21, and these are pretty important for your May-June 22 series, okay? So make sure you do these. I'm gonna link the March 22 paper up as well. So there has been changes to the syllabus. Okay, not everything from here is included in 2022 anymore. We don't have communications anymore. We don't have op amps, no operation amplifiers. We do not have MRI anymore. We also do not have what else? Yeah, that's more or less it. MRI, communications, operation amplifiers, analog, digital, those conversions. We don't have those, and we don't have band theory, right? But a few things have been added. Astronomy has been added, right? And PET scanning has been added to medical physics, and discharging a capacitor has also been added. Okay, let's begin. So, starting with question number one. It's a 1 mark question. They're asking us what is meant by centripetal acceleration. So, if they ask you this, it's basically centripetal acceleration is the acceleration that is perpendicular to velocity. Because look at this diagram I have down here. When the toy car is moving to the right, the centripetal force is directed towards the center. When it's moving up, the centripetal force is still directed towards the center. Do not use the words towards the center though. You should prioritize saying perpendicular to the velocity. Okay, it's always 90 degrees to the direction of the velocity v. Remember that. Now let's try to understand B1. An unpowered toy car moves freely along a smooth track that is initially horizontal. The track contains a vertical circular loop around which the car travels, as shown in figure 1.1. So the mass of the car is 230 grams and the diameter of the loop is 62 centimeters. Assume that the resistive forces acting on the car are negligible. So no work is done against resistance. And what is happening? As the toy car is moving up the loop, it is actually gaining gravitational potential energy and losing kinetic energy. Okay, so this is the energy conversion. Initial K is being converted to final K and some gain in Gp. So the final K is less than the initial K. That means there's a decrease in velocity. Now think about it. Centripetal acceleration is v squared by r. So if velocity decreases, acceleration will also decrease, right? That's the logic behind this. What happens to the magnitude of centripetal acceleration as it moves from x to y? The centripetal acceleration will actually, it decreases, alright? Now the next one is a bit more difficult. For this, we need to understand the basics of a loop. At the bottom, normal contact force is directed towards the center, weight is directed down. So the difference between normal contact force and weight is the centripetal force. When it is moving vertical up, I'm talking about this case, weight is directed vertically downwards and normal contact force is towards the center. So only N is providing the FC. At the top, both weight and the normal contact force, right? Both of them are in fact directed towards the center. So both of them are providing the centripetal force. Okay. So basically, at the top, you are most likely to fall down. Does that make sense? At the top, you are most likely to fall down or lose contact. But at the bottom, normal contact force works very hard to keep you moving. Do you understand? So at the bottom, n has the greatest value. Think about it. Here, n is equal to w plus fc, and at the top, n is equal to fc minus w. Okay, that's the logic. At the top, n is equal to fc minus w. Do you understand? So now it's better to explain. Look, I have some diagrams here. This is what happens. At the bottom, it's the difference between the two. At the top, it's the summation of both. Okay. And here's working showing that at the bottom, normal contact force has the highest value 70.3. At the top, it's 60.3. So I'm going to tell you the logic right now in multiple ways. So at y, they're telling us, explain if the car remains in contact with the track, why the centripetal acceleration of the car at y must be greater than 9.1 at y. Let's see this. weight and normal contact, both of them are providing centripetal force. So when do we lose contact? Just think about it. You will lose contact when the value of n is actually 0. At that point, W is equal to Fc, right? Or mg is equal to mv square by r. We get rid of m. G is equal to v square by r, or 9.8 is equal to the acceleration of the centripetal acceleration. Okay, so if acceleration is 9.8 or below this value, if the centripetal acceleration is 9.8 or below this value, do you understand what's going to happen? It's going to lose contact, because I just figured out that when n is equal to 0, when normal contact force is 0, like what does it literally mean? Normal contact force means the force that is keeping you in contact with the surface. So when normal contact force is 0, you will lose contact. So I equated weight and centripetal force and found that at this value we will lose contact. Now think about it. We cannot possibly let W. So when do we lose contact? When do we lose contact? Basically, basically when the weight becomes greater than centripetal force, we lose contact. Okay, so if 9.8 is greater than the centripetal acceleration, if acceleration is less than 9.8, we will lose contact. So remember, to stay in contact with the surface, centripetal force must be greater than the weight. Okay, to be in contact, this is the golden rule. Centripetal force must be greater than the weight. Mg greater than mv square by r. We get rid of m. So acceleration, centripetal acceleration is basically greater than 9.8. That's what we need. I can show you another way. Check this. So I taught you this, right? At the top, n plus w is equal to centripetal force. N is equal to centripetal force minus weight. So we basically want n to have a certain value. So since it's the difference between centripetal force and weight, for n to have a value, right, centripetal force must be greater than weight. Then we're going to get a positive value. It will contribute to the centripetal force, right? So that's the logic. Okay, so how are we gonna word this actually? So the best way to say this is centripetal force must be greater than weight. So remember this formula over here, W plus N is equal to Fc. So centripetal force must be greater than weight. Why? Because we do not want n to be 0, because if n was 0, centripetal force was going to be equal to weight. That's the logic. But if n is not 0, think about it, this value will be a value greater than weight, and centripetal force will take that value, which is actually greater than 9.8. So for centripetal force to be greater than weight, it requires some contact force. It requires a value of n. Okay, this will only occur when n is present and Fc at that moment is equal to n plus w, because if n wasn't there, centripetal force would be equal to weight, and that wouldn't be enough to keep us in contact. The trolley would actually fall down. Okay, so for centripetal force to be greater than weight, it requires contact force from the track. Okay, so it was quite a complicated answer. And remember this, guys, that you could word this in another way. You could say that acceleration of 9.8 is caused by weight of the car. That's an alternate for Mark 1. You could say that A of 9.8 ms minus 2 is caused by weight of car. So for the acceleration to be greater than 9.8, we require a contact force from the track. That's the logic. Okay, that was an alternate route. For centripetal acceleration to be greater than 9.8, it requires contact force from the track. Okay, so hopefully I made it clear. It's a bit difficult, but I guess you could understand. Next, the initial speed at which the car moves on the track is 3.8. Determine whether the car is in contact with the track at point 1. Important, important. So basically, in a loop, you will have minimum speed at the top. Okay, in a loop, you will have minimum speed at the top. Remember this. Always. In a loop, you will have minimum speed at the top, because I taught you, right? As you go up, GP increases, K decreases. So speed also decreases. So at the topmost position, you'll have least K, right? So I'm gonna show you this in a few ways. Let's do the math first. So what's happening? Initial K, half m Vx at position x, right? Half m Vx square. Initial K is equal to final K, half m Vy square at the top, plus the GP mgh. Okay, so we can actually get rid of m. We can get rid of m. Half m. What's the speed at x? 3.8. Sorry, half into 3.8 square is equal to half into Vy square plus 9.81 into, what is the height actually? The diameter is 62, right? So this is also, the height is also 62 cm or 0.62 meters. Yeah, so half Vy square, or let's multiply everything by 2 actually. Vy square is equal to 3.8 square minus 9.81 into 0.62 into 2. Vy square is equal to 2.2756. So what is Vy? Vy is actually root over this, which is 1.51, 1.51, or 1.5 basically, 1.5 meter per second. So we need to determine whether the car is in contact. So what can we do? Now we can find out the acceleration at y. What is the value of centripetal acceleration? It's v square by r, right? So I'm using my calculator answer, and what is the radius of the track? It's 0.31 centimeters. So acceleration is equal to, at the top, 1.51 square divided by 0.31. So answer square divided by 0.31. That's giving me a value of 7.3 ms minus 2. So since our acceleration 7.3 is less than 9.8 meter per second square, we actually lose contact, or it loses contact basically. Okay, so no contact. So no contact. This is what you'll write. Okay, so this is one way of doing this sum. There's another way. You could actually find out the minimum speed required. Okay, you could actually find out the minimum speed required to be in contact by working backwards. Do you want me to show you the other route? Let's go with route 2. This is for the same question, route 2. Basically, what we're gonna do is, we know that a is equal to v squared by r, right? 9.8 is equal to v squared by 0.31. What's the value of v squared? I mean v. V has a value of 1.74. This is the velocity at y, by the way. So now let's find out the velocity at x, right? So half m vx square is equal to half m vy square plus mgh, or half into vx square is equal to half into, I got rid of the m's, by the way, half into 1.74 square plus 9.81 into 0.62. Let's solve this. So I'm getting a velocity of 3.9 meter per second. So I need this minimum velocity so that I can have a minimum velocity of 1.74 meter per second at y. But what's our velocity? It's actually 3.8. Okay, so since our initial velocity 3.8 meter per second is less than 3.9, so no contact. That's the other way of solving it. Okay, really important. Next, suggest with a reason but without calculation whether your conclusion C would be different for a car of mass 460 grams. Thing is, as you can recall, I cut all the m's. Okay, so actually mass cancels. Get it? Mass cancels in the equation. So it actually makes no difference. Remember that. Okay, or you could go for this. Acceleration is independent of mass because a is equal to v squared by r, right? So it makes no difference. All this for 8 marks. You have to be kidding me. But I just have some tips for you. In the exam, if you're stuck, just skip that, right? To get an A star, you need something like 80 marks. 75 to 80 typically. Okay? And the threshold for A is at like 60 to 65. 55 to 65 even. Let's go to number 2. State the relationship between gravitational field strength and potential. So gravitational field strength is equal to the negative of minus potential gradient. Okay, just like electric field strength is minus potential gradient, it's the same way here. Okay, so gravitational field strength is gm by r square and gravitational potential is minus gm by r. So that's basically it. Okay, gravitational field strength is minus potential gradient, electric field strength is minus potential gradient as well. Remember that. Moon of mass m and radius r orbits a planet of mass 3m and radius twice r. At a particular time, the distance between their centers is d. Point P is a point moving along the line between the centers of the planet and the moon at a variable distance x from the center of the planet. Okay. The variation of x of the gravitational potential phi at point P for points between the planet and the moon is shown in figure 2.2. So let's check this. Let's try to understand what's happening. So we have a moon on the right hand side and we also have the planet on the left hand side. This point P is variable, it moves between these two lines, right? So always remember the variation in potential between two planets will always be this inverted U, and the variation in field strength will always be like this. There will be a neutral point in the middle because gravitational field lines are directed radially inwards, right? So they are in opposite directions, so they cancel out at one point. Okay, remember that. So explain why phi is negative throughout the entire range. Okay, really important question. So this is a common question. Remember that potential is actually 0 at infinity. The highest value that potential can take is 0, which is at infinity. And gravitational forces are attractive. You know that when you drop a ball from a height, right, the ball loses GP, right? So if the maximum value is 0, and if you come closer due to the attractive forces, what is a value that is less than 0? Won't it be negative? Right? So since 0 is our maximum value, and when two objects come closer together, since it's an attractive force, work is got out. It needs to lose energy, right? So when a test mass gets closer from infinity, it actually loses potential energy. So when a test mass gets closer from infinity, it actually loses potential energy. Okay, so this is really important, guys, for 2022. This is the new mark scheme for this apparently. So potential is 0 at infinity, Gravitational forces are attractive. So when the point mass, the test mass moves from infinity to a point inside the field, or inside, the distance inside the line between these two the planet and moon, it will actually lose potentiality. One of the features of figure 2.2 is that phi is negative throughout. Describe two other features of figure 2.2. So there are 4 points in the mark scheme, it seems. We just want to describe this, okay? So the potential at the surface of the planet is smaller than the potential at the surface of the moon. So let's look at the planet. If we assign a scale, this is -1, this is -2, this is -3. It's at like -3.2-ish, right? What about this? It's at wait. It was at -3.1-ish. It's -3.1, yeah. And this is at 1, 2, 3. It's at -2.3 or something, yeah. So for the planet, the value of potential at the surface of the planet is smaller or more negative, okay? Next, what else? Let's look at the potential gradient or the field strength. Look at the tangent, right? The tangent is steeper for the planet, right? So the potential gradient at the surface of the planet, wait, for the moon, it's actually steeper for the moon. My bad. Check the tangent. Here, the tangent is like this, right? For the moon, it's like this. It's a bit steeper. Just look at the angle it makes. Look at the angle. Clearly, this angle is greater than this one over here, right? So the smaller the angle, the steeper the gradient, right? There's more change in y compared to change in x with respect to change in x. So the field strength is actually steeper at the surface of the moon, or you could say that the potential gradient at the surface of the moon is greater than the field strength or potential at the surface of the planet, or vice versa. The potential gradient at the surface of the planet is smaller than at the surface of the moon. That's what they wrote, okay? You could also go the other way around, it's fine. Next, the magnitude of potential actually varies inversely with a distance from center near the spheres. That's the property of potential. Phi is equal to minus gm by r. Since mass is relatively constant, g is also a constant, it actually varies inversely with r. Okay, remember that. This is what we're seeing. Alright. So this is point number 4. I did not write this. This is another point 4. The magnitude of potential varies inversely with distance from center near the spheres, okay? This is from the mark scheme. The magnitude of potential varies inversely with distance from center near the spheres. And last but not least, the magnitude, yeah, that's it. That's more or less it. And the last one, the point of maximum potential is nearer to the moon than the planet. Check this out. The point of maximum potential. What's the maximum potential at? Around this value, right? This is 0.9, 0.8, 0.7. It's like 0.65, between 0.6 minus 0.6 and 0.7, right? It's like minus 0.65. Look at the distance between the planets. It's 0.5 boxes, 1.5, 2.5 here, then 1, 2, 2.5 boxes at the center. So there are 5 boxes in total, and the midpoint is at 2.5 boxes, right? So the point of maximum potential is actually nearer to the moon. So I'm going to teach you something. The point of the neutral point will also be closer to the moon, because the one that has a smaller mass, it will have a harder time to cancel out the force, right? So obviously at the midpoint, the force from the planet, the bigger mass will be greater. So always remember, in case of potential and field strength, the field strength will be 0 closer to the smaller mass. The potential will also take maximum value closer to the smaller mass. This is fixed for all questions, okay? So the point of maximum potential is nearer to the moon than the planet, right? Now they want us to draw the variation with x of gravitational field strength. Pretty straightforward. So I just chose this one to be positive, right? That's why this is negative. You could draw it the other way around. That's totally okay. Okay, you could draw it the other way around. Next, let's go to the other part. So what do they want? Basically, the one curve starting with gradient of decreasing magnitude at 2r and finishing with gradient of increasing magnitude at d minus r. Okay. There is a mistake though in my diagram. The field strength for the moon should be greater. The field strength for the moon should be greater. And there should be zero potential at the point of zero field strength at the point of maximum potential or near to it. Okay, so I'm gonna draw the exact figure now. See if you can follow. So there's maximum potential here at 0.5, 1.5. It's between these two, right? Somewhere here. 1, 2, 3, 4, 5. Yeah, 5 boxes from the midpoint. Okay. So 0.5, 1.5, 2.5. This is our midpoint. 1, 2, 3, 4, 5. This is the point that had maximum potential, so there's going to be zero field strength at this point. Okay. Now, what about the field strength? It will be higher for the moon. Okay, since the gradient was steeper. 1 boxes, 2 boxes, 3 boxes, 4 boxes. And what about this? 1, 2, 3, 4. So why don't we use 3 over here and 4 over there? That's going to be fine, right? So I'm going to go with 3 over here and 4 over here. Okay. So let's go with neutral point over here. Right, it looks good. Doesn't have to be absolutely perfect, but it should be something like this. This is the perfect diagram. Okay, this is the perfect diagram. And yeah, that's it. Why, by the way, why at 2r and why not from here? That's really important. Basically, you need to understand something. Gravitational field strength inside the object is actually 0. Okay, so it has to be from the surface. Make sure you remember that. Okay, so you cannot actually exceed this. Okay, remember that. Moving on. Question 3. What is meant by an elastic cohesion? So there is no loss of kinetic energy in that collision. Okay, that is an elastic cohesion. So one assumption is all collisions involving molecules of the gas are elastic. What are the other assumptions? We have multiple assumptions. This is what I prefer. No intermolecular forces between molecules, right? Obviously, except during collisions. What else? The molecules have negligible volume compared with the gas, with the volume of the gas or the volume of the container, basically, right? Then what else? Molecules are in random motion, right? And collisions are instantaneous. Okay, so let's go to B. By the way, if you like the content, please remember to subscribe, because a lot of you are not subscribed. Like the number of unique viewers are increasing, but the gap between subscribers and non-subscribers are also increasing. So remember to subscribe. A molecule of an ideal gas has mass m and is contained in a cubic box of side length L The molecule is moving with velocity u towards the surface of the box that is shaded in figure 3.1. The molecule collides elastically with the shaded face and the face opposite to it alternately. These expressions in terms of m, u, and l for the magnitude of the change in momentum of the molecule colliding with the face. Okay, so when it hits this face, it hits the wall with u, and then it rebounds with the same speed u, but in the opposite direction. So what's the change in momentum, del p? That's actually, if we consider the left side to be positive, it's going to be mu minus, then the right side will be negative, minus mu. So it actually adds up to twice mu. Okay. The time between consecutive collisions of the molecule with shaded face. So the length of one side is L, right? And we know that it's constant speed. So S is equal to Vt. So time is equal to distance by velocity. So the distance is L and the velocity is u. But there's a catch here. What's the catch? Basically, the time between consecutive collisions of the molecule with the shaded face. So hear me out. Basically, we want to find the time gap between consecutive collisions with the shaded face. Okay, so why can't we use L? What's the issue actually? Basically, let's assume that the molecule, where is it located right now? Suppose the molecule is located over here at this surface. Okay, the molecule is initially located here, for example. Now it's moving towards that wall. All right, just after one collision, it's moving towards that wall. It has to cover this distance L. Okay, now after it hits that wall, it still has to travel this distance L again. So after one collision, right, it has to travel the distance L to get to the other wall, and then after colliding with that wall, it needs to come back through this distance L to collide again. So if we think of this as time zero, right, we are actually traveling the distance L twice for two consecutive collisions. Okay, so it's actually this time taken between consecutive collisions. You can't only think of one, you need to think about two over here. Okay, and now the time between two is like the time taken after you collide once. You're gonna collide one time, and then the time taken to collide one more time. Okay, so that's what they mean, that's what they want. So suppose you're on the wall on the left hand side, you just collided, the timer starts. Now you're going to move towards the wall on the right hand side, you're going to collide with it, and then you're going to go towards the wall on the left again. So you have to travel the distance L twice. That's the logic behind this. So the time will actually be 2L divided by U. Now you might be asking, why the wall on the left hand side? Why didn't you start from the center? Okay, let's start from the center. That's fine, but you need to start your timer from this point onwards. Like it has to complete one oscillation. It's kind of like that. Okay, so you go here, that's L by 2. You collide, then you go through L again, and you come back and travel L by 2 again. Okay, but it's best to start right after you collided once. That's the best thing to do, right from here or something. Okay, moving on. The average force exerted by the molecule on the shaded face. So for the next part, we know that force, the average force is equal to the rate of change of momentum, right? From AS, change in momentum by time. So the change in momentum is twice mu, and the time is twice L divided by U. So we can get rid of 2, and we end up with mu squared by L. That's it. So this proof was actually in the it's in your coursework, okay? This example should be in your lectures. You should be reading this, okay? The pressure on the shaded face if the force in 3 is exerted of the whole area of the face. So we know that pressure is actually equal to force by area, right? So the force is mu square by L. And what about the area of one face, right? Suppose this face. That's L into L or L square, right? So what do we end up with? We actually end up with mu square by L cube. Mu square by L cube. That's it. Now, the derivation. When the model described in B is extended to 3 dimensions and to a gas containing n molecules, each of mass m, traveling with mean square speed c square, it can be shown that PV is equal to 1 by 3 nmc square, where P is the pressure exerted by the gas and V is the volume of the gas. Use this expression together with the equation of state of an ideal gas to show that the average translational Ke of a molecule of an ideal gas is given by this equation. So we know that PV is equal to nkt. So nkt can be equated with 1 by 3 nmc square. Now here's the thing, we can get rid of n and we can multiply 3 on that side. 3 kt is equal to mc square. We know that the average kinetic energy of one molecule is going to be half mc square. So we can do some manipulation. We can bring a half on each side. Half mc square is actually equal to 3 by 2 kt. And this half mc square is actually equal to the kinetic energy, average translation energy of one molecule. So that's it. Okay. The mass of a hydrogen molecule is this. Use the expression to determine the root mean square speed of a molecule of hydrogen gas at 25 degrees Celsius. Okay. So half into 3.34 into 10 power minus 27 into mean square speed is equal to 3 by 2 into Boltzmann constant 1.38 into 10 power minus 23 into the temperature in Kelvin 25 plus 273. Let's solve this. So the mean square speed is 1.02 into 10 to the power 1, 2, 3, 4, 5, 6, 7. If you want to find out the RMS speed, the root mean square speed, basically CRMS, the value is going to be root over answer, which is 3189 or 3200 to two significant figures. Okay. Wait, I messed up the calculation a bit. 1 second. Let me check. 3 by 2, 1.38 in 10 power minus 23. Yeah, sorry, the value of c square was wrong. It's 3.7 into 10 to the power 6, right? After you root over this answer, you're going to get a value of 1921, which is rounded off to 1.9 into 10 power 3. We need to give our answer to two significant figures since our data has a minimum of 2 SF. Okay, that's the logic. 2 is almost always fine. Okay, let's move on to question number 4. 4 is a bit complicated. A trolley on a smooth surface is attached by springs to fixed blocks as shown. This is a question of simple harmonic motion. The trolley oscillates horizontally about its equilibrium position with an amplitude of 12. Figure 4.2 shows the variation of the acceleration A of the trolley with displacement x from its equilibrium position. Friction between the trolley and the surface can be assumed to be negligible. Okay, so no energy is lost since it's a smooth surface. Describe the features of the line that demonstrate the motion of the trolley is simple harmonic. So mainly it's a straight line passing through the origin. This indicates that acceleration is proportional to the displacement. And the negative gradient indicates that acceleration and displacement are in opposite directions. You should write that. They didn't write it in this mark scheme, but it's typically there, right? Now use figure 4.2 to determine the period of oscillations, t. We know that a is proportional to minus x, or a is equal to minus omega square x. So you can take any random values. Suppose I just went with when a is equal to zero point 0.8. Suppose when a is equal to plus zero point 0.8, the displacement is minus 12, right? Or in meters, 0.12. So zero point 0.8 minus zero point 0.8 equals to minus omega square into 0.12. Omega square is equal to 0.8 by 0.12. 2 pi by t whole square is equal to 0.8 by 0.12. 2 pi by t is equal to root over that. So time period is equal to 2 pi divided by answer. We're getting a value of, this was, wait, 0.8 by 0.12 is around 6.67. Root over answer is 2.58. This value is 2.58. So t is equal to 2 pi by answer, which is 2.4 seconds to 2 significant figures. Now, these are a bit difficult. On the line of the graph of figure 4.2, label with the letter P one point where the kinetic energy of the trolley is 0. So remember, in simple harmonic motion, you will have 0 Ke when you have maximum Pe. That is at the ends, okay? So at maximum displacement, you are momentarily at rest. You may have maximum acceleration, but you are momentarily at rest. So kinetic energy is actually 0 at that point. So you have two options for labeling P, either here or here. Just go with one. Don't label both. Could I clarify? Just go with one. Okay, that's it. Now the next one. On the line, label with the letter Q an approximate position of 1 point where the kinetic energy is equal to the potential energy. This is a bit weird. So logically, our mind would be thinking, okay, so the maximum displacement is 12. Our it should be half at 6, right? Isn't that the logic? But it doesn't work like that. Why? Because the kinetic energy actually depends on the value of v square. It's actually proportional to the value of v square, not v. Although potential energy, yeah, it just varies with the square. That's the issue. That's why it's not a linear scale. So let's actually find it out. How are we gonna do it? So the potential energy is half m omega square x square, while the kinetic energy is half m omega square x naught square minus x square. How did I get this? We know that velocity at any point is omega root over x naught square minus x square, and k is half m v square. So if we square v, we end up with v square, and we get rid of the root, right? So v square is actually equal to omega square into x naught square minus x square, okay? So this is the Ke and Pe. So we want the Ke to be equal to Pe, right? And we know that potential energy plus kinetic energy is equal to the total energy. And we want the Pe to be equal to Ke. So for that to happen, we can substitute one of these in over here, right? Since I want the Pe to be equal to Ke, we were looking for that point. I just substituted it inside. So Pe plus Pe is equal to total energy, and 2Pe is equal to Te. The total energy is half m omega square x naught square, and the potential energy is half m omega square x square. We can get rid of half m and omega square, and we end up with twice x square is equal to x naught square. Why did I choose Pe to be substituted? Mainly because the kinetic energy one is a bit more complicated, right? Also, I want to find out this value of x. X naught represents amplitude, while x just represents the displacement at any point, right? So 2x square is equal to x naught whole square. So x naught is 12 centimeters. X square is equal to 144 by 2. And root over answer is 8.49. So the exact place where k is equal to Pe is 8.49. Okay, so it's gonna be somewhere over here. This is 6, this is 8, this is 10, and this is 9. So it should be between 8 and 9, somewhere here, okay? Either this one, or you could go for that side. You could opt for that one as well. So they just wanted it to be, they just wanted anywhere here, in between this. In between more than half, but less than maximum. Okay, they didn't want a quantitative one, but if they ever do ask for one, you know how to do it now, right? So this is super important. Moving on to 5. 5 is not in our syllabus anymore. Okay, so moving on to 6 then. What is electric potential? Electric potential is basically work done per unit charge. It's basically the work done per unit charge to do what? To move it from infinity to a point inside the field. But work done per unit, you have to say it's the work done per unit positive charge. Okay, so the best way to write this answer is actually the work done in moving per unit positive charge from infinity to or the point inside a point inside the field. That's what I prefer. Okay, a point inside the field. This is my preference. An isolated conducting sphere in a vacuum has radius r and is initially uncharged. It is then charged by friction so that it carries a final charge q. This charge can be considered to be acting at the center of the sphere. By considering the electric potential at its surface, show that the capacitance of the sphere is given by this. Alright, let's go for it. We know that capacitance is equal to charge stored on each plate divided by voltage between the plates, and we also know that voltage is equal to 1 by 4 pi epsilon naught into q by r. So if we substitute this inside here, what do we end up with? C is equal to Q divided by 1 by 4 pi epsilon naught into Q by R, right? And these Q's can be cancelled out. So we end up with, after reciprocal, 4 pi epsilon naught into R. That's it. Okay? Shown. The dome of an electrostatic generator is a spherical conductor of radius 13 centimeters. It is initially charged, so the electric potential at the surface is 4.5 kilovolts. A smaller sphere, isolated sphere of charge, radius 5.2 centimeter, initially uncharged, is brought near the dome. So this is the dome, and this uncharged sphere is brought closer. Sparking causes a current between the two spheres until they reach the same potential. Assume that any charge on a sphere may be considered to act as a point charge. Okay, so the laws are valid, and the charge initially this had a potential of 0. This had a potential of 4.5. Now the potential is the same for both spheres basically. Okay, so let's try to do this. Come on. This is for part C. So the logic is the formula for potential, we don't use that because we have this new formula over here. This is for the potential at its surface, at the surface of the sphere. We know that Q is equal to 4 pi epsilon naught into R. Okay, so for the bigger sphere, what was the charge in the first place? 4 pi into the value of epsilon naught is 8.85 into 10 to the power minus 12 from the data booklet, right? Into its radius is 0.13. Okay, so this is the capacitance. Actually, this is the capacitance. I'm actually finding out the capacitance, but you do know that Q is equal to CV, right? For a capacitor, this is valid. So if you want to find out the charge, what do you need to do? It's basically 4 pi into 8.85 into 10 to the power minus 12 into 0.13 into the voltage of the sphere, which is 4500. We are getting a value of 6.51 into 10 to the power minus 8 coulombs. Okay, that's what I got. 6.5 into 10 to the power minus 8 coulombs. This was the initial charge. So here's the thing, guys. Potential can change, okay? Potential won't be divided equally, but charge cannot be destroyed. Charge has to be conserved. Remember Kirchhoff's first law? It follows the law of conservation of charge, okay? So what's the logic behind this? Check this out. We know that C is equal to 4 pi epsilon naught into r, and we also know that q is equal to cv. We know these two relations. So what's the difference between these two spheres? The radius varies, right? That's literally it. Only the radius varies. This thing is a constant, so we can say that capacitance is proportional to r, right? Capacitance is proportional to r. So the greater the radius, the greater the capacitance. Also, we know that C is equal to QV. C is equal to QV. And if we consider, like, they have been brought to the same potential, this is the most important part. V is the same for both of them, right? V is the same for both of them. So it's like this, Q by C is equal to constant V. And C is proportional to R. So what can we write? Q by R is equal to constant. So Q1 by R1 is actually equal to Q2 by R2. So what happened to this, the charge for the bigger dome? Charge decreased, and for this one, charge increased. So we can actually say that Q minus small q divided by R1, which is 0.13, or just 13, in fact, both of them are in centimeters, is equal to just small q, the increase in charge, divided by 5.2. Okay, that's what we end up with. Or 6.5 into 10 to the power minus 8 minus q divided by 13 is equal to q divided by 5.2. Let's solve this. 13q is equal to 6.5 into 10 power minus 8 into 5.2 minus 5.2q. Or if you bring it to that side, 13 plus 5.2q is equal to 6.5 into 10 to the power minus 8 into 5.2. Let's solve this. I'm getting a value of 1.9. Q is equal to 1.9 into 10 to the power minus 8 coulombs. Okay, this is one way of doing it. So this is quite a complicated sum. This variant was in fact difficult, so you should do this properly. I'm going to show you an alternate route though, right? Let's learn the alternate route. What other way did we have? This is route 2. So basically we can think of it as one capacitor. So we know that Q is equal to CV and V is equal to Q by C. Total voltage equals to total charge by total capacitance. I just told you guys, charge is not destroyed. So what's root 2 after you get this value, right? 6.51 into 10 power minus 8. What can you actually do? You can write that the total voltage is actually equal to the charge, the total charge we calculated, 6.51 into 10 power minus 8 divided by the total capacitance, which is, remember, capacitance equals to 4 pi epsilon naught into R. So what's the total capacitance going to be for both of them? 4 pi into epsilon naught, 8.85 into 10 power minus 12 into R, which is the radius of both of them, basically. 0.13 plus 5.2 centimeter, which is 0.052. So if you do find this out, right, you're gonna get a value of total voltage of 3210 volts approx. Now this is the same potential that both of the spheres have, right? We can use this to do what exactly? We know that C is equal to this and Q is equal to CV, right? So we have an idea about the voltage. Now we can find out the charge. Charge is equal to 3210 voltage into 4 into pi into 8.85 into 10 to the power minus 12 into the value of R, which is 0.052. If you solve this, let's not write this as Q. let's denote it as small q. So small q is going to be equal to 1.9 into 10 to the power minus 8. This is also another route that you could take. I prefer the one I showed you at the beginning, okay? So we don't have 7 either. Op amps have been excluded, okay? No 7. So we have 8, 9, 10, 11, 12, 5 more. So let's start with 8. So two long straight parallel wires P and Q carry currents into the plane of the paper as shown in figure 8.1. The current in P is I and the current in Q is 2I. Okay. So remember that current carrying wires, if they carry current in this sorry, if they carry current in the same direction, they're gonna attract. Okay. So since both of them are carrying currents out of the plane of the paper, oh sorry, into the plane of the paper, a cross means into and a dot means out of. So they're going to attract. So the one in P is I, the one in Q is 2I. On figure 8.1, draw an arrow to show the direction of the magnetic field at Q due to the current in P. So guys, use your right hand. Use your right hand grip rule to find the direction. So your right hand should point into the plane of the paper. If you're pointing your thumb into the screen like I am right now, you should get field lines like this. What do these mean? Clockwise field lines. So they want you to show the direction of the magnetic field at Q. Q is just a location due to P. So it's due to the wire, something will always get priority. So I'm actually giving priority to P. The field lines are like this then. So at Q, what will it be like? It will just go like this. Get it? So remember, we are giving priority to P now, and the field lines will actually be like this, right? It's a circle and it's clockwise, so it should go like this, something like this. Now we just have to show the one at Q, so it's gonna be like this. It's gonna be vertically downwards, okay? And we are labeling this as B. That's all. Arrow pointing vertically downwards at B. Next, draw another arrow to show the direction of the force acting on wire Q due to the current in P. So since they're carrying current in the same direction, the force will be attractive. So the force should point in this direction. We will label this as F. State with a reason how the magnitude of the force acting on P compares to the magnitude of force acting on Q. Basically, guys, do you know the formula? The force is actually, you know that it's BIL, right? So the force actually depends on the products of both of the currents, the current in Q as well as the current in P. Okay? And it's inversely proportional to the distance between them. We don't need to memorize the formula. We will be asked to derive it with given information. But I mainly want to teach you that it depends on the products of the currents, not only one. As a result, it will follow Newton's third law. So we can say this, the force is proportional to the product of both currents. That means I and 2I. Or we could just say that due to Newton's third law, forces are equal in magnitude, right? Equal in magnitude. But there's a catch. They're in opposite directions, okay? But that we don't need to write that down here. If it was 3 marks, you'd write that down. But basically, they want how the direction compares. We're just going to say that the direction will be opposite. Okay, cool. Moving on to 9. What is the photoelectric effect? Basically, it's the emission of electrons from a metal surface when electromagnetic radiation is incident on the surface, on the electrons of the metal surface, right? So what is the work function energy? It is basically the minimum energy of electromagnetic radiation, right? Minimum energy of electromagnetic radiation required for an electron to leave the surface, right? Leave the surface of the metal with 0 Ke. They did not write this in the mark scheme. I prefer writing it. But if you write minimum, it's fine. A polished calcium plate in a vacuum is investigated by illuminating the surface with light. It is found that no photoelectric current is produced when the frequency of light is less than 6.93. So state the name of the frequency below which no photoelectric current is produced. These are basically properties of particle nature, not wave nature. So what is this frequency called? It is the threshold frequency. Explain how the photon model of electromagnetic radiation accounts for this phenomenon. Interesting. So, mainly, what should we say? We should say that photons are actually packets. Photons are discrete packets or quanta, right? Of electromagnetic radiation or just energy. What does the energy depend on? The energy of photons depends on the frequency of electromagnetic radiation. And here's the thing, one electron can only interact with one photon. That's the very important point. Okay, it's very important. Like one can interact with one. Even if you have a lot of, well, you have one photon with lots of energy, it can only give rise to one electron. Do you understand? So electrons can only absorb a single photon of energy. Important. Calculate the work function energy of calcium. So the work function is denoted by phi. It's actually equal to hf naught because there's no Ke, right? So the value will be 6.63 into 10 power minus 34. This is from the booklet into 6.93 into 10 to the power 14. We're going to get an answer in joules, 4.59 into 10 power minus 19 joules. To convert joules to electron volts, you need to divide by the elementary charge, 1.60 into 10 power minus 19. So we are getting a value of 2. So our data is 3 Syrian figures. We should also give our answer to 3SF. 2.87 electron volts is fine. Okay. Moving on to 10, 11, and 12, last three. Figure 10.1 shows a simple laminated iron core transformer. This is a step down transformer because the secondary coil has lower number of turns, 25,000 to 625. State the function of the iron core. It mainly helps to increase the magnetic flux linkage between the coils. Okay, why is it laminated? The lamination, it's plastic basically, so it actually reduces energy losses. Why? By reducing the induced eddy currents. So lower currents mean lower heat will be generated, right? So now we are tasked to find out the output voltage. The input PD is a sinusoidal alternating voltage of peak value. Now they want you to find out maximum value. Okay, so we're going to use peak. If they don't mention anything, you're going to use VRMS. Since they mention max, you're going to use max. So we're going to use the formula V in by the number of turns in primary coil is equal to V out by number of turns in secondary coil. For current, it's at the reciprocal, though it's the other way around. So 12,000 divided by 12 kilovolts, 12,000 volts divided by 25,000 turns is equal to V out divided by 625 turns. So if you do the math, you're going to get a value of 300 volts. Okay. Moving on, calculate the root mean square current in the load resistor. So we can find out the peak current using V is equal to IR. The resistor is of 640 ohms. So 300 is equal to I naught into 640. I naught is equal to 300 by 640. That's our peak current. Now we know that RMS current is equal to I naught by root 2. So 300 by 640 divided by root 2 gives us a value of 0.33 amperes. Okay, great. Now the tough one. Let's do this. On figure 10.2, sketch the variation with time of the power P dissipated in the load resistor for time 0 to 40 milliseconds. Assume that when P is equal to 0, T is also equal to 0. Hear me out. Power can never be negative because P is equal to I square R or V square by R. Even though current or voltage was sinusoidal, right? They took negative values, but when you find out power, it's gonna turn into a positive value basically. Or even P is equal to VI, minus is plus, right? So they gave you this part below just to trick you guys. Don't get tricked. So let's find out maximum power first. We know that P is equal to V square by R. We know that V naught is 300. So it's 300 square divided by 640 ohms from above, right? 300 square divided by 640 ohms. So this is our peak power, 140.625 watts, or just 140. Now think about this. Our voltage was sinusoidal. It had a period of 40 milliseconds. It was like this. It had a period of 40 milliseconds. So half of it was at 20. You reached peak value twice every period, right? Check this out. You reached it once here at 10, you reached it at 30. Even though it's negative, since it's going to be squared off, it doesn't really matter, right? It's kind of like rectification. Power is going to take the positive value. So the value, the graph for power will be like this, something like this basically. So we're going to reach a peak every time at 10, 30, 50, 70, like that. But it won't be 100% like rectification. Why is that? The curve actually takes the function of cos square, okay? It's squared off, right? So if you square sine or if you square cos, do you know what graph you're gonna get? You're gonna get smooth transitions. So you cannot draw a graph that's like this, okay? You cannot draw a graph that's like this. You have to draw a graph with smooth transitions, like a cos square graph basically, okay? So you're gonna get peak values at 10, 30, and you're gonna get a value of 0 at 0, 20, 40, 60, so on. 0, 20, 40, 60, and so on. Okay, so those are the basics. Wait up, it's glitching. Yeah, so hear me out. This is how I draw the graph. So I basically find these values out, that there's going to be 0 power at 0, 20, and 40, and there's going to be a peak at 10. These are the values I got. Peak at 10 and 30. Then I just draw smooth transitions and fill them up, okay? This is the graph we get, the green one. That's all. Now this one was a bit tricky. Explain with reference to 10.2 why the mean power is 70. Interesting. Check this. Check this. So multiple ways I can show you. Remember this graph? This is sinusoidal current maybe, or voltage. So remember we used the RMS value Y, because if we found out the mean voltage for a sinusoidal voltage graph, the average value of voltage would be 0 actually, right? Because since it's symmetrical about this midline, it will take this value at the midline, which is 0. So that's one way of thinking of it. Look at this. This is basically a sine graph with a midpoint in between 140 and 0, which is in fact at, wait a bit, so yeah, the midpoint is between 140 and 0, which is at 70. So if you think of this graph over here, the current, since the midline was at 0, the average value was 0. Since the midline here is at 70, the average value will also be 70. Okay, this is because the power curve is symmetrical about the midpoint. That's the reasoning. That's why it takes a value of 70, 140 divided by 2. There's another logic, by the way. If Vmax is a V naught square by R, what will the average power be? We're going to use VRMS whole square by R. VRMS is V naught by root 2. If you square that, you're going to get a value of half into V naught square by R, or basically half into maximum power. Always remember that average power will be half the maximum power, but you need to give this reasoning. This is because the power curve is symmetrical about the midpoint, okay? Difficult to answer. Okay, final questions now. 11 and 12. What is the function of the piezoelectric crystal? It basically acts as a transducer, okay? It generates ultrasound at first by resonance, right? It generates ultrasound. What else? It's a transducer, so it also detects reflected ultrasound. Now, how are we creating the ultrasound actually? Basically, the reasoning behind part 1 is the applied alternating PD causes the crystal to vibrate. That's the logic, or you could just opt for saying how it detects ultrasound. Basically, the ultrasound that comes back and hits the crystal causes vibrations, right? Vibrations cause crystals to generate an EMF. So do you get why it's called a transducer? It works both ways. This is the crystal. If you apply PD, it will create ultrasound. Also, if you give ultrasound, the vibrations will create a PD. Do you get it? So any one of these, this for 1 mark, this is 1 mark, this is 1 mark. Important. Define specific acoustic impedance. It's basically the product of density and speed, product of density and speed of ultrasound in a certain medium. Okay, so it's the product of density and speed of ultrasound in that medium. Describe qualitatively how the specific acoustic impedances of two materials affects the intensity reflection coefficient alpha, z1 minus z2 whole square divided by z1 plus z2 whole square. So look at this. Suppose this is muscle and this is bone. This one going here is I naught. Some of it will get out, that's IT. Some of it will be reflected back in IR. So alpha is basically IR by I naught. So if the values of Z1 and Z2 are very similar, okay, most of it will be transmitted. So if you can say that if similar or if same, then most of it is transmitted, right? So what happens to the value of IR by I naught? It will be close to 0, right? Then the reflection coefficient is either 0 or very low. So if I'm going to write down the scenarios, if Z1 is approximately equal to Z2, IR by I naught or alpha is approximately equal to 0, and at the same time IT by I naught is approximately equal to 1. Next, if very different, what will we see? Then reflection coefficient is nearly 1. Okay, you need to understand this. If very different, most of it is, if either z1 is much greater than z2 or z1 is much less than z2, then IR by I naught or alpha is actually almost equal to 1, or IT by I naught is approximately equal to 0. None of it is transmitted basically. So what can we do to wrap this thing up, this explanation? The lower the wait up, the lower the difference, means the lower the difference, the lower the reflection coefficient. Okay, please check your course book though. I don't think they call it alpha anymore. They have different wording. It's a bit different. Just check it out. Okay, moving on to the last question, then we're done. This is also a bit difficult, right? So what is meant by radioactive decay is both random and spontaneous? What is random? we cannot actually predict when a particular nucleus will decay, right? Or we actually cannot predict which nucleus will decay next. So we cannot predict when a particular nucleus will decay, or we cannot predict which nucleus will decay next. What about spontaneous? So it means that decay is not affected by external environmental factors. Common questions. Now, a sample of radioactive material contains atoms of an unstable nuclide X. The activity of the sample due to the atoms of X is A. The variation with time t of ln H shown in figure 12.1. Okay. Use figure 12.1 to determine the half-life in minutes of nuclide X. Let's do this. So, according to the equation, A is equal to A naught e to the power minus lambda t. If we bring ln on both sides, ln A is equal to ln A naught e to the power minus lambda t. Right? So, ln A is equal to ln A naught plus ln e to the power minus lambda t, or ln A is equal to ln A naught minus lambda t. We can get rid of ln E. So if you look at the graph, on the y-axis we have ln A, on the x-axis we have t. We can rearrange it to write ln A is equal to minus lambda into t plus ln A naught. So ln A naught is actually our intercept, and minus lambda is the gradient. Okay, so let's find out the half-life. How? We know that the gradient is minus lambda, so you can use appropriate coordinates to find out lambda. I used 36.4, 0, 36.4, and 20, 35 point, what, 20, 35, 20, 35.0. Okay, so it's 35 minus 36.4 divided by 20 minus 0. We're getting a value of minus 0.07, or lambda is equal to 0.070. So if you want to find out per minute, if you want to find out half-life, it's ln 2 by lambda. So half-life is equal to ln 2 divided by 0.070. It gives us an answer of, wait, let me tell you the exact one. 9.9, 9.90. So for some reason they wrote 10 minutes. I don't really know why. It's 9.90 exactly. Okay, ln 2 divided by 0.070 is 9.902. This should be rounded off to 9.1 to 2SF. I don't know why they wrote 10. I'm not exactly sure. Maybe it's in minutes or something. This is an anomaly. Don't trust this. Anyway, there was another way. It's much more complicated. You could find out the intercept from this. You could find out the intercept from ln A naught. So A naught is equal to e to the power intercept 36.4, right? Ln A naught is equal to 36.4. Ln A naught is equal to 36.4. So how does that help us? A naught is equal to e to the power 36.4. A naught is equal to 6.43 into 10 to the power 15 becquerels, right? You could find that out. And then you could use A is equal to A naught e to the power minus lambda t, where you could find out A naught by 2. Okay, you could get a half-life. You could basically read off the half-life. You can actually figure out when we get half the activity of the original time, and we could read it off as 10. Okay, because A naught by 2 would be what exactly? 6.43 into 10 power 15 divided by 2, right? Which is 3.2. A naught by 2 is 3.215 into 10 power 15. Now if you find out the value of ln A naught by 2, how much is that? Ln answer is 35.7. So if you look at 35.7, where is it? This is 35.6, and 35.7 is somewhere here. So it is a value of 10. You could read it off from the graph. That also works, okay? I guess that's why they wrote 10. Now the next one is a bit difficult. This is a bit hard, okay? So at time 0, the mass of the atoms in the sample is this. Determine the nucleon number of X. Interesting. So at time 0, we know that the activity is ln A naught equals to 36.4 from the intercept, and A naught is equal to e to the power 36.4. Where am I getting this? From the rearrangement of the equation at first, okay? Now A naught is equal to 6.43 into 10 power 15. This was the initial activity. Now we know that A is equal to n lambda. We can use A naught is equal to lambda n naught. We can find out the initial number of atoms of the nuclide using A naught by lambda, which is 6.43 into 10 power 15 divided by lambda. But careful, the lambda we found out at the beginning, that was in per minute. Okay, that was 0.070 per minute. You need to convert this to SI units, which is per second. So 1 minute has 60 seconds. So we need to give 60 here. This is lambda in per seconds. That's why I divided that by 0.070 by 60. We get a value of n is equal to 5.51 into 10 to the power 18. Okay, it's still not done yet. So the mass is 5.66 into 10 to the power minus 27. We need to find out the nucleon number of X. How to do this? So remember this, that this is a nuclide, right? This is a nuclide. It has an atomic number and a nucleon number. Atomic number Z and a nucleon number A. So the total mass, okay, this is the formula. Total mass is equal to mass of one nucleus into total number of particles. That's what I applied here. The total mass 5.66 into 10 power minus 27 is equal to the number of particles into the mass of one nucleus. Okay, so let's go for it. Five point six six into 10 power minus 27 minus 7 kg is equal to the number of particles into mass of one nucleus. So 5.66 into 10 power minus 7 divided by n is equal to mass of one nucleus. So what's the mass of one nucleus actually? How would you find this out? It's actually the nucleon number into the mass of one nucleon, which is U, 1.66 into 10 power minus 27, right? So we know the value of n, which is 5.51 into 10 power 18. So if you divide 5.66 into 10 to the power minus 7 divide by n, 5.51 into 10 power 18, you're gonna get the mass of one nucleus. And the mass of one nucleus is equal to, I just told you, the nucleon number into U. So it's like this. You can write it like this. Nucleon number into U is equal to 5.66 into 10 to the power minus 7 divided by 5.51 into 10 to the power 18. Alright? Or the nucleon number into 1.66 into 10 to the power minus 27 is actually equal to 1.03 into 10 to the power minus 25, followed by this step over here. If you make nucleon number the subject, you're going to end up with 1.03 into 10 power minus 25 divided by 1.66 into 10 power 27, which gives us a value of 61.8 or 62. This was one of the most complicated radioactivity or nuclear physics sums. Okay, so do this properly, and if you have any other questions, let me know. That's it for this variant. I'm gonna upload okay, just check this math out once more, all the working. Like I showed you an example, how do you find out the mass of alpha? It's 4u, right? We just applied the same logic over here. Yeah, so I'm gonna upload October November variant 41/43. It's the same one. Okay, by tomorrow I'm gonna link it up here. Okay, this is variant 41 or 43 over here, and I'm gonna link the Feb March 2020 paper down below if you need that, and the playlist for P4 will be up here. And remember to subscribe to the channel. Alright, keep on supporting, and if you have other questions, just let me know. And tell me if you want other questions solved. The exam is on 10th, so I don't think there is much time, but I'll still try. Okay, see ya.